So before we start, we have to ask ourselves a very important question. Then what potential should we actually consider to explain the magic numbers, right? So that is important. So since in talking about electrons and when we talk about the quantum model and all, we have seen that potential is important to be considered so that we actually know what is the energy that is involved. Okay, so what kind of potentials are there that we might have already studied? Okay, so we have already studied few potentials, and let me just list some of them. Okay, and let's see which one we should actually consider. So we have I'm going to discuss only about four potentials here. Okay, out of which two of the potential you have already studied. Okay, and the other two we are going to discuss in this particular part. So the first potential that we have, okay, if you remember, is a square well potential. Okay, it can be a finite square well potential or an infinite square well potential. Okay, so a square well potential, that's the first one. The second potential, if you remember, this is also very important. I hope you have done it. If you've not done it, I think you can revise it a bit. A harmonic oscillator. Nuclear physics is such a topic that you really can't explain it without knowing about quantum mechanics. Okay, so we need to know about harmonic oscillator. Okay, the third potential that we are going to deal with, which will explain the potential inside the nuclei better, is Woods-Saxon potential. That's actually the important part of your syllabus. Okay? And the fourth one is nothing but the Woods-Saxon potential again does not explain the total magic numbers. So what we are going to do is we are going to take Woods-Saxon potential plus the spin orbit interaction. So LS coupling, if you remember from atomic physics, we are going to understand that. Okay. So we are going to take up these four potentials and we are going to check that why this, and this does not agree with the magic numbers. It cannot explain the existence of magic numbers, but this one clearly explains the existence of magic numbers. So please remember this image so that if I'm asking you a conceptual question or an objective question on this, you'll be able to answer. Okay. But you know, it's a long topic, so obviously it's going to take up some time. But before we start, let me just give you one concept, which is again, I think important, and I hope all of you remember. So the nuclei is divided into shells, and we have got the subshells. Okay, so we have got the subshells as S, P, D, F, and here we can take the value of L is equal to 0. This is 1, this is 2, this is 3, and so on. And the maximum number of electrons that we can actually have in a subshell is 2 into 2n plus 1. Based on that, we can actually draw the energy level diagrams. Okay, and if these are the subshells, the shells are nothing but K, L, M, N, where you know this is 1, this is 2, this is 3, this is 4. So these are all nothing but the principal quantum number. Now, if you want to write down the electronic configuration and someone, let's say, write down something like 1s. Let's say someone is writing it down as 1s. Okay. So you simply know that this will actually represents the K shell, okay, and this will actually represent the S subshell. Okay, so in this way you can actually identify both the principal quantum number, which is n is equal to 1 in this case, and the azimuthal quantum number where L is equal to 0 in this case. Okay, so this is how you can actually identify and also write down the electronic configurations and all. So I hope you can recall these things. Okay, now the next thing is, what exactly do we mean by energy level diagram? So the electrons will be there at the ground state. And if we consider the Pauli's exclusion principle, we know all the electrons cannot be there in the ground state because it violates Pauli's exclusion principle. No two electrons with same quantum number can exist. So that means it has to go to the next energy level. Maybe this will be the next energy level, and then it will be the next energy level, and so on. And we know these energy levels are also not equally spaced. That is also very important, right? So what we have along this direction is nothing but energy. In this direction, we basically have the energy. So I hope you can recall this. So let's say at the ground state, we can have how many? Let's say 2 electrons, right? So we can say that this is nothing but the 1s state. Okay, why 2 electrons? Because it's 2 into 2 into L is 0, S state L is 0 plus 1. So it is going to have 2. So next state, so this can be written as 1s. So let me write it down 1s on this side, I think. And then I can have, let's say 1p, for example. And here I can have it number of electrons as 2 into 2 into 1 plus 1. So it is 2 into 1, 2 plus 1, 3 into 2 is 6. 6 number of electrons. So it is 1, 2, 3, 4, 5, 6. All of them will have different quantum numbers. Spin up, spin down, different azimuthal quantum number and so on. Right? SP, then we can have T, and here we can, T is nothing but 2. So it is 2 into 2, right? So we have already done it. 2 plus 1, 4 plus 1, 5, which is equal to 10. So this will be 1D, and it can actually have 10 electrons. 3, 4, 5, 6, 7, 8, 9, 10. Right? So and so on. And in this way, you can actually fill up the energy levels. Okay. So this is exactly how the electrons will occupy their positions depending on which shell and which subshell they are in. Okay. So this is something which we already know. So this is the idea of concept that we're using here. Now let's go back to the idea of potential. So the first potential that we are going to consider, okay, so that we are able to say that which energy level the electrons will occupy is nothing but the infinite square well potential. So the first potential that we are going to consider is square potential infinite. Okay? And I hope you recall what is an infinite square well potential. If you are inside a room and there is no door as such, I'm just giving you an example, you won't be able to escape the room. That means for you, escaping the room is impossible. That means the potential outside the room is infinity. You cannot be there. But you can be inside the room and you can roam around inside the room. So V would be equal to 0, right? So in simple words, we can say that the potential is equal to 0, okay, when we have r as less than r naught. The distance is less than r naught. So maybe I can say this is r and this is r naught. You are trapped inside this room, which is r is equal to 0 and r is equal to 1. And it will be infinity if you are going outside, right? Similar to a square well potential, if you remember, you did it in case of harmonic, I mean, in case of square well potential in quantum mechanics, and you also found out the energy. You remember if you did it, okay, you found out what was the wave function. Psi is equal to root over of 2 by L sine of n pi x divided by L. If you remember, that's the wave function that we had, and the energy was n square h cut square divided by 2 ml square and so on. So there you use the condition that Vr is equal to V naught inside and outside it is 0. That means it can escape. It was a square well potential but not infinite, right? And then you can find out the energy. Similarly here also you can solve the Schrodinger equation and find out what is the energy available, okay? But we are not going to do it because we are just going to understand the concept. We are not going to solve it. You can check the quantum mechanics book for solution for this. Now, if we basically solve for E, okay, we can plot the energy level diagram. We can plot energy level diagram. Okay, so understand this. This is important. Energy level diagram. So that means we can say how many energy levels would be there, what will be the energies at which each of these levels will be, and so on. Okay, for doing that, let's plot one energy level diagram very easily. So let's say this is the first energy level, second energy level. And of course, they are not equally spaced. We know it because it's all quantized and so on. Fourth energy level and so on. Okay, so I'm not drawing all the energy levels here. And let's say we are having, this is your 1s state. Okay. This is your 1s state. This is 1p, then 1d, 1f, and so on. 1d, 1f, and so on. And let's see if we can actually fill these levels. We're filling with the maximum number of electrons possible. So at the lowest level, we have got 2 number of electrons. I'm just writing down the values directly. In p state, we have already seen how many number of electrons will be there. It will be 6. So there will be 6 number of electrons in the p, and in d it will be 10, right? And in f it will be 14 and so on. So when we talk about magic numbers, that means the outermost orbit should be full. And if you're talking about the 1s state, the number of electrons that we have here is 2. And please recall what are the magic numbers that we have, okay? The magic numbers, I hope you remember, okay? Sometimes it's important. So it is 2, okay? And then 8, 20, somehow we have to remember this, right? 50, 82, and so on. So these are the number of electrons that should be there, or protons and electrons that should be there for magic numbers. So it is 2, and next number we have got is 6 in p state. So if you add them up, that is the number of electrons. Total is 8, not electrons. Here we are talking about protons or neutrons because we are talking about the nuclear model. So please remember, these are representing the number of protons and neutrons, okay? Not electrons. Should not be electrons here. So it is 6 plus 2, it will be 8. And then let's add up the next one. It will be 6 plus 2, 8. 8 plus 10 is 18. Right? Okay. And then we have also got the F state. F state. Okay. And in F state also there can be, as per the definition, it can actually split into two energy levels. And what will happen is one of these energy levels will be very close to D. So there will be 2 electrons here. Okay, let me just do a bit of correction here. Okay, and here it will be not. This will be F, so it can be 14. But 2s state, 1s, 2s is there. The 2s state will come here, very close to D, if we draw the energy level diagram. So these two will form very close structure. And the total number here is nothing but 12. Okay, they are very close to each other. So we can say that they are in a single shell. So that means if we add them up as well, is this, not 18, sorry. It's 6 plus 2, 8. Okay, 8 plus 12. So this is total 12. So this will become 20, not 18. So it becomes 20. If you go to the next one, it's 14. And if we add them up, it will be 20 plus 14. So this will be 34. And so on. Okay, you can keep on adding up. And let's see. So check this. This is 2, which is a magic number. This is 8, which is a magic number. 20 again is a magic number. Okay, so these two are there. These three are there. But 34 is actually not a magic number. This is not a magic number. That means if you're talking about heavier elements, the square well potential cannot explain magic numbers. That is the important concept here. Okay. So for light elements, I hope you understand. For light elements. What do you mean by light? You see 20. That means there are 20 numbers of protons or neutrons. Okay. So maybe example, Z is equal to 20, less than equal to 20. Okay. It can explain. But for heavy elements, it can explain. Okay. The magic numbers are explained. But if you are considering heavy elements, okay, Z greater than 20, okay, magic numbers are not explained. So that means we cannot take a square well potential to explain the idea of magic numbers. Okay, so that means that is not something which is practical when we are considering a potential inside the nucleus. Okay, so what we are going to check next is there any other potential which is possible? So the second potential that we are actually considering is harmonic oscillator. So harmonic oscillator, let's check. Okay, once let's check for harmonic oscillator potential. So if we again plot a diagram for harmonic oscillator, we are going to see something here. Harmonic oscillator. Let's check for harmonic oscillator. Okay. So again, we are not going to do much of maths here in the case of harmonic oscillator as well, but we are going to solve it. Okay, we are going to solve it, and if we solve it, for harmonic oscillator, this is something which you might have done. The energy that is actually calculated is nothing but E is equal to n plus 3 by 2 into h cross omega. Okay. Here this n, okay, if you look into the problem in quantum mechanics, you'll see that this n can take the value 0, 1, 2, and so on. Okay, because even if you put n is equal to 0, you are not going to get this energy to be 0. So it's fine. That means ground state also it will have some energy. Remember, if you're considering an electron, proton, neutron, whatever, if it's in the ground state, it's not that its energy is 0. That's not okay. It has an energy, but it is more or less stable in nature. Okay, and also this n, if you look into the problem, it can be written as 2 into the principal quantum number plus the azimuthal quantum number. That's the solution for this. Okay, but anyway, we're not going to discuss the solution. Okay, now let's see what are the possibilities in this particular case. Okay, when can n be equal to 0? Okay, so let's check one by one. Now, when can n be equal to 0? There are two possibilities, only one possibility here, that small n should be 0 and L should be equal to 0. Okay. Now, if you look into the convention here, when small n is equal to 0, that means we can take the principal quantum number to be 1 because this is considered to be the ground state here in this particular case. Okay. And this L is equal to 0, L is equal to 0 corresponds to the S state. Okay, please remember this L, S, S, P, D, F, okay, and so on. So when L is equal to 0, that means it is S state. Okay, next just check for N is equal to 1 and let's see what are the possibilities. N can be equal to 1 when this small n is equal to 0 and L is equal to 1, right? So this is again n is equal to 0, so it will be 1 shell, and the subshell L is equal to 1. Okay, so maybe I should write it down somewhere so that we all get all it easily. S, P, D, F, and so on. So this L is equal to 1, 2. So when L is equal to 1, it is P, so I can say this is the 1P state. Okay, let's go for the next value. These are all integral values. N is equal to 2. N is equal to 2. Now there are two possibilities. The first possibility is n is equal to 1 here, n is equal to 1 here, and L is equal to 0. That can be written. So L is equal to 1 means we are going into the second shape, and L is equal to 0 means it S, so it is 2S. What is the second possibility? The second possibility is n is equal to 0 and L is equal to 2. So that means these two energy levels will be together, okay? Because it's giving you for the same value of capital N, okay? So here we can basically say that this is n is equal to 0, that means it's 1, and L is equal to 2, L is equal to 2 refers to the D state. So 1, that's it. Okay, let's go for the next one. N is equal to 3. When we're talking about n is equal to 3, that means again there are two possibilities. This small n is equal to 1, L is equal to 1, right? If you put n is equal to 1, it is 2 plus 1, so it will be 3. So that's 3. So that means n is equal to 1 means it's 2 here, and L is equal to 1 means we are talking about the P state. So we can say 2P. And let's look into the next possibility. We can say n is equal to 0, okay, and L is equal to 3. So n is equal to 0, L is equal to 3. N is equal to 0 means it's the first K shell, and L is equal to 3 means we're talking about the S state. So I can say 1F. So that means 2P and 1F are together, 2S and 1D are together, and so on. Okay, let me write down one more energy level here. Let's write down for n is equal to 4. And here also we are going to see that there are going to be two possibilities, the three possibilities in fact. N is equal to 1, it is 2L plus 1, okay? So 2N plus L, sorry, 2N plus L. So we are going to have N is equal to 1, one possibility, and L is equal to 2. So it will be 2 into 1, 2 plus 2, which is equal to 4. So it is N is equal to 1, so that is 1, 2. N is equal to 1 is 2, second K L shell. And L is equal to 2, L is equal to 2 matlab B. So this is D. So let's look into the other two possibilities. The next one might be I can take L is equal to 2. So 2 into 2, 4. That means L is equal to 0. So that means this is 3. L is equal N is equal to 2 means it's the M shell, KLM N shell, sorry, N shell. L is equal to 0 means S. And the third possibility might be N is equal to 0 and L is equal to 4. So 4 we have not written here. So F after that it will be G, and for G it will be 4. So that means for N is equal to 0, this is 1 and this is G. Now see, we have the values, okay? We have the values now, okay? So we have the values now, okay? More visible, yeah. So now we have got N is equal to 0 and we get the values of the energy states that we have. Let's now draw the energy level diagram. Let's draw it. So maybe one. I'm considering N is equal to 0, N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4. And take these energy levels now. I think it's not very complicated to understand. I think it's easy. So N is equal to 0, capital N is equal to 0. We have got just one state, that is 1s. So let me just write it down here as 1s. Then N is equal to 1. We have got again just 1, that is 1p. So I will write it down here as 1p. N is equal to 2. I have got 2s and 1d. So I can write it down here as 2s and 1p. And then we have got N is equal to 3 is 2p, 1f. So 2p, 1f. And then finally N is equal to 4, 2d, 3s, 1g. Right? So I can write it down as p, 3s, and 1g. And let's write down how many electrons can be there. So in the 1s state, it will be 2. Okay, so not electrons, protons or neutrons. Okay? There will be 2 number of protons or neutrons. And 1p, it will be 6. Right? And then 2s and 1d, right? So 2s, again, it's the s state. So we can actually have 2. And d will basically have 10. It is 12, right? 2p and f, okay, p can have 6 and f can have 40. So it will be 6 plus 40. And let's go for g, okay. This 2d, so d can have 10 number of electrons, plus s can have 2, plus g. So it is g, so that's 4, right? So it will be 2 into 2 into 4 plus 1, so that should be 18. 8 plus 1, 9, 9 into 2, 18. So it will be g state, it will be 18. So let's see what are the shells and how they are getting filled up. So in the first energy level, we have got 2 electrons, fine, magic number. If you're considering these two, 2 plus 6, that's 8, magic number. Let's consider these 3, 8 plus 12, so that's 20, fine as well. Let's go for the next energy level. That is 20 plus 6, 26 plus 40, which is 40. So that's not a magic number. That's actually a semi-magic number. But then again, doesn't come under the category of magic numbers. Okay. And so this 30, I guess. Yeah. 18, 20, 30. So 30 plus 40, that will be 70. Again, not a magic number. So this is 70. Right. So you see, it explains these magic numbers. This is a magic number, this is a magic number, this is a magic number. But then beyond that, again, it cannot explain this. It cannot explain this. So what do we conclude from here is that both harmonic oscillator and infinite square wave potential, these are infinite potentials, and they are not able to explain the magic numbers in the shell model. So in order to explain this, we need to consider a finite potential. And in the next class, what we're going to see that Woods-Saxon potential is much closer to reality. And when we use spin orbit interaction along with Woods-Saxon potential, it's going to explain the magic numbers. We are also going to, but this time we are going to derive it, okay? And we are going to plot the energy level diagram, and we are going to see that it actually explains the magic numbers, okay? And that will be actually something which is very important. It's more or less a descriptive section.